that the lowest exam gets replaced by the final exam, which ideally you're not using your first exam as that whiff, but so some of you feel some pressure now to sort of just stay focused. Is it possible to still pass the class with a great grade? Yes. Just if you bomb one exam, it's not going to kill you. But that said, if you bomb the first exam, that means a couple of things. One, it means you're not doing enough work. So that's first thing. And in this class, 5-credit class, you really should be spending outside of the class time a minimum of 15 hours a week. That 15 hours a week usually is for someone that came in well prepared. If you come into Calc 2 and you have a bunch of holes in your trig and a bunch of holes in your college algebra, that 15 hours a week is not going to cut it. And the 3 classes that kind of are the gauntlet, Calc 2, Calc 3, Physics 2, those 3 courses are, very serious, heavy lifting classes that if you don't have good study skills, either you have to be a genius or you got to get real lucky. And it's unlikely that you're going to get lucky and just have questions that you happen to know how to do. So you really have to adjust your study skills. It's like this course is the beginning of courses that really, it's kind of a joke that it's a 200 level course. It's much more like a 400 level major course. And it's like there's so much math that has to happen. If they spread Calc 1, 2, and 3 out like they did a humanities sequence, it'd be like 6 classes, right? I mean, there's no way you're going to spend anywhere near the same amount of time in a Calc 2, Calc 3, or Physics 2 that you spend in any humanities or social science class. It's just, the way these classes are built is just, they're so packed because you could get practically a degree if you spread this class, if you spread calculus out how it should be. But so it's super intense that way. And you just have to get into that mindset of, I'm doing calculus 5 nights a week. And if I don't get it, I'm going to do more. Because it's one of those subjects that's super hard. And Calc 2 in particular is hard because we use all the algebra and all the trig. Calc 1, you can skate with knowing, having some holes in your algebra, having some holes in your trig. You can skate through Calc 1. Calc 2 and 3, no way. Every page has trig on it in Calc 2 and Calc 3. So you've got to make sure you go back to those prereq things and get those down. And of course, you need to have good Calc 1. You have to be able to take derivatives. Almost every problem in Calc 2 and Calc 3 starts with a derivative. If you blow the derivative on the first step, you're hosed. It's just like it's bad news. So good news is if you had a low score, you can replace it with your final exam. Bad news is that means you've got to ratchet up your studying even more because it's not going to get easier. The hardest exam, most people say in all of calculus, is our 3rd exam when we get to the infinite series and the infinite sequences. That's sort of considered the hardest material in all of calculus. Some people would say the hardest material in all of undergraduate possible topics is the infinite series part. That's a very difficult subject. So what you should do, the key and the test are up here in OneNote. So you really should go through it very carefully. There's 2 things you should do. You should go through the exam very carefully, go through the key very carefully while it's fresh in your mind, while you still have your 2 hours and 15 minutes of suffering close at hand, readily accessible. That's the best time to look at the key and to really figure out what did I miss? Why didn't I, get full credit or those types of things. The other thing you should do is make sure that I added up your points correctly. And if you look at your score, the way I do grading is really different than probably most teachers that you've had. And if you go to our grading guidelines document, which is under handouts, grading guidelines, this explains to you exactly what I'm doing. I take 1 point off for a trivial mistake. If you I wasn't super vigilant this time, but in the future, as we do more and more, 1 point for something trivial. Trivial, like you forgot the units. Trivial, like you took the square root of 7 and said it was 2. Whatever. Trivial mistakes, things that are not conceptual. And then I take off 2 points for any conceptual error. You know, if you think you should have done pi r squared and you use the diameter instead of the radius, that's a concept error. And so then you'll lose 2 points. And frequently, if you have 2 conceptual errors, I'll just give you 0 unless the problem had some math that was correct. Then I might give you a point just for your effort if it was correct math. So then I add up all those points and I divide by the number of questions on the test. So you'll see the denominator is 13 because we have 13 questions. So it's very similar to a GPA style of grading. So then this is the way that I go back to a percentage. If you get a 5, 5 on every question. So if you got perfect on every question, that's 100. If you end up with an average of 4, that's 90%. A 3 is 80%, a 2.5 is 70, a 2 is 60, a 1 is 50. And then below that is whatever it turns out to be. So that's how I am grading it. Some people say, oh, it's a built-in curve. You can think of it that way if you want. For me, I feel like it's just a pretty accurate reflection of what you're doing. When I went to CU, I was in the engineering program and the math program over at CU. And you take these exams in these big exam halls, and you get your test back, and it says 68%. It says 68% on it. You're like, oh crap, 68, not doing well. You head straight to the bar. Your fake ID works. You're like, okay, this sucks. And then you get back to class the next time, you find out you got a B. And in my mind, if somebody tells me I got a 68, but then I get a B, I don't feel like I'm a B student. I feel like I'm a D student. It doesn't feel right. So I don't like that model of grading where everything is curved so dramatically. I would rather have the grade that I'm given reflect the knowledge that I have. And that's why I developed this system, because I feel like it's very accurate in that way. It has some built-in curved nature. If you have 10 questions, you can miss 2 and get an A, and you can miss 4 and get a B. So it has a little buffer there. If you have 2 questions and you fully understand one, and you don't understand the other, what happens? If you get 100% on one question and a 0 on the other, that averages to 50%, which is an F. That, to me, is not reflective of what somebody's understanding is. If you really understand one problem and don't understand another one at all, to me, that's C knowledge. That's like, okay, you got half of it. That's not an F understanding of the concepts that have been presented if there's only two concepts presented. So that's kind of why I grade it this way, so that for me, it feels like it's just more accurate. No need to do any curving. And you can see, oh, I took 2 points off here because I missed a concept. I took 1 off because it was trivial. And those trivial errors aren't going to add up to, doom your score if you forgot units here and there. So that's kind of what it's about. So look at your test carefully. Look at the answer key. Double check the numbers. But more importantly, look at that answer key, because we have a lot of math going forward that doesn't necessarily depend on what we've done. But if you can't do the integration stuff, that's a problem, because this class is all about integration. So let's go ahead and go to, first I want to go to our schedule, because we have a slight modification. Our slight modification, because we lost a day, is this. And we're kind of lucky that we have been told by the state of Colorado that we should cover 9.1 and 9.2 which is a very basic introduction to differential equations. And we're going to skip these two sections now. That is which is fine, because anyone going on in engineering has to take DiffEq, and they start from the beginning as if you've never seen a differential equation in your life. So it doesn't really matter. Most of us feel like it shouldn't be in here anyway, because you're going to treat differential equations. Every one of you is going to take a full differential equations or maybe combo with linear algebra, and you start from the beginning. In these sections, we just learned the most basic differential equations. And the simplest differential equation is solved by integration. That's what integration does. It solves differential equations. So that's what we're already doing. There's just a terminology that needs to be adjusted a little bit. So we are just shifted a day. So we aren't going to cover this. Everything is just shifted a day. So today we're going to do 8.1 and 8.2, and we're just going to continue on. The review will still be on this day. Our exam 2 will still be on that day. On 3.6, we'll just be covering the 8.5 and 8.9 stuff. So the only difference is that we're crossing out 9.1 and 9.3, and everything is just shifted today. So that's how we're going to deal with our fire drill. It was a fire, a real fire. Okay, so if you have any questions on that, let me know, and I will answer them. So we are starting in chapter 8 now, general integration. And I want to point out some things. So we have these integration tables, these integration pages are in all of our calc books, often in physics books also. And we know that anytime we have a derivative formula, it leads to an integration formula. When you say the derivative of sine is cosine, that's equivalent to saying the integral of cosine is sine. So that's an important thing. So if we look at secant, we know the derivative of secant is secant times tangent. So the integral of secant times tangent is going to be secant. And of course, there is this, what I have been referring to as the reverse chain rule thing going on in all of these. The reverse chain rule piece, everyone aware of that? Like there's an AX, so we're dividing by the A. The integral of sine is minus cosine. But we have to divide by the derivative of the angle. So that's the reverse chain rule piece. All of these have that reverse chain rule piece. There's an AX up there. The derivative of AX is A. Integral of an exponential is itself, but then we have to divide by the derivative of the exponent. So that reverse chain rule piece is reflected in all of these. This one, we are going to see, of the 3 inverse trig functions, we will see that one the most. So the integral of dx over a squared plus x squared will be that. We will see this one the second most of the inverse, the ones that integrate to an inverse trig function. And this one we're going to see the least, the inverse secant. So you really want those two down, those two that, and I'll show you why those integrals are what they are. But you'll want to get those two, of the ones that integrate to inverse trigs, those two down. This one most important. You're going to see that so many times. And that one's interesting because the inverse tangent function for most of us is the first function we see that has 2 horizontal asymptotes. So inverse tangent has that look. Now, a couple observations. You know sine and cosine, how to integrate them. They essentially integrate to each other. There's the minus sign, of course, but they're essentially integrating to each other. When we look at the other 4 trig functions, when we come down here and look at the integral of tangent, the integral of cotangent, the integral of secant, and the integral of cosecant, do you notice that they all 4 of those integrate to, what I've highlighted in blue, to natural log functions? They all integrate to natural log functions. And I want to just look at that for a minute. So if we were to look at the integral of tangent x, we can rewrite this as the integral of sine over cosine, if we use our whatever they call it, that identity, the quotient identity, maybe they call it. So we have this setup now. That is almost in log form. If all 4 of these integrate to logs, what that tells me is that I should be able to do a little manipulation to create an integrand that's in log form. Log form, the denominator's derivative is the numerator. That's log form. If the denominator's derivative is the numerator. What's the derivative of cosine? Negative sign. So I'm going to make it exactly the derivative of the denominator. But if I multiply the inside by -1, multiply the outside by -1 to balance it, right? So I'm going to do this. Now it's in log form. Now it's in log form, so we know that this being in log form will be -1 natural log of the absolute value of the denominator. That makes sense? And of course, you're probably looking at it and saying, hey, that's not what they have there. It's not what they have there. But what can you do with this little thing right there when it's sitting in front of a log? What's the log property? If you have a coefficient in front of a log, how can you manipulate it? Yeah, it gains wings and flies up as an exponent, right? It can fly up to here as an exponent. And what is cosine to the -1? Secant. 1 over cosine. Right, so that -1 comes up there, so you can write it either way. And it does not matter to me if you're coming up with this. Both those are totally fine. They're the same. Does not matter. Now let's take a quick look at cotangent. So the cotangent function, when we look at that, there, is it in log form? Is the denominator's derivative the numerator? Yeah, it's already in log form. We don't have to do any massaging. It's ready. So the denominator's derivative is the numerator, so right away we know that this integrates to natural log absolute value of sine x. So that's how we do those two. Those two are a little bit easier than the next two. Let's look at secant, because this does show up quite frequently, the integral of secant. Now, if we are going to end up with a log, that tells me I should be able to do a little massaging of that integrand to put it in log form. Well, right now there's not even a fraction. So I'm going to multiply, and we always multiply by 1, right? That's how we manipulate things. That's how we change the look but not the value when we multiply by 1. It's like that dimensional analysis stuff in chemistry. All right, if you 12 inches to a foot, 3 foot to a yard, you just do things. You change the look but not the value. You change the units. Same idea here. We want to multiply by 1 to change the look but not the value. And this takes a little bit of ingenuity here to understand what to multiply by. The way I remember what to multiply by is to ask myself, what is the derivative of secant?
Secant x tangent x.
Secant x tangent x. And here is the form that we are going to use. If you multiply by secant x plus tangent x, it's not the derivative. The derivative is secant times tangent. But that's just like a mnemonic to figure out, to remember that, oh, if I multiply by secant plus tangent, watch what happens. So if we multiply top and bottom, secant plus tangent, that's just 1. Haven't changed the value, just changed the look. So let's see what happens in the numerator. We end up with secant squared x plus secant x tangent x. all divided by secant plus tangent. Is it in log form? What's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. It's now in log form. As soon as it's in log form, we're done. Once we have a fraction that we're integrating that's in log form, this is natural log absolute value of the denominator. Plus c. Question?
How do you know that it's going to be in log form?
Because the integration tables are showing that the antiderivatives for all the trig functions, other than sine and cosine, are logs. So if I know, if somebody says, oh, this is going to integrate to a log, then I go back and I say, oh, well, then I should be able to manipulate this and put it in log form. Anything that integrates to a log is coming from a fraction where the denominator's derivative is the numerator. Right? From the very beginning, that's not how it was described to you in Calc 1, but from the very beginning, that is the pattern here. That's log form. What's the derivative of x? 1. Right? That is the pattern. That is log form. So if we generalize it, the idea is that if we have a function in the denominator and its derivative in the numerator, that will always integrate to this if you did substitution. Let u equal f, then u prime is going to be f prime of x dx. You'll get the integral of 1 over u, which is natural log of u, and then you back substitute. So anything that integrates to a log, the integrand should be possible to write it in log form. This one is going to come up so much. The cosecant one comes up from time to time, and you can fiddle around with it, at your leisure. The secant one comes a lot. We are going to see the integral of secant a lot. You're going to write down that answer a lot this semester. And it's going to become automatic. But, well, it has to become automatic, but this is why. So play with that a little bit and just sort of, you should be able to get it down. All right, so that's kind of the main idea with these integration tables. We've got all those summaries. Let's take a look at another one that we want to summarize. So this one, see what my percentage view is. This is something I want this to be 100. So we've already talked about these. The book kind of preemptively threw in an integral that included one of these. And I told you have to use power reduction identity. And these are the formal power reduction identities. Anytime we see a sine squared or a cosine squared, in order to manage that integral, we have to reduce the power. And one thing that you're noticing is that as you reduce the power, you're increasing the angle. But an increased angle is simple to deal with, right? An increased angle, if you're integrating cosine of 5 theta, d theta, right? Isn't that easy to integrate? You end up integrating the outer function. The integral of cosine is sine of the same angle. And then all we do is divide by the derivative of the angle, right? So a big angle, not a problem. Big power, that's the problem. That's the thing that's difficult to manage for sine and cosine. Obviously, if it's secant squared, there's no problem there, because we know the derivative of tangent is secant squared, so the integral of secant squared is tangent. But for sine and cosine, if we have a power, we need to reduce the power. And, where do these formulas come from? They come from the doubles. If you look at the two alternate forms of the double angle, so right here, if you isolate cosine squared, and right here, if you isolate sine squared, that's where those come from, right? So if you isolate those two, you will see. If you add 1 to both sides, divide by 2, subtract 1, divide by -2. That's where they come from, the double angles, the alternate double angles. So let's take a look at this. So here, right away, I see, oh, power of 2. I need to reduce the power. And the way you write you can do this in lots of different ways. You could factor out the 1/2 right away. Lots of different numerical ways to do it. So, but in general, you just have to replace that. So, and hopefully you're noticing that these things are identical, except for one is a minus and one is a plus. They're both cosine. They're both divided by 2. So you just need a way to sort of remember which one has the minus. Whatever works for you. The thing I was taught and never forgot was that with sine, you have the minus. If you think of sine as sin, sinning is negative, usually. So maybe not when you're a freshman in college. I don't know. But that's how I remember it. Someone told me that long ago, and I can't forget that. So whatever it takes. Sine has the negative, cosine has the positive. And in both of these, the natural next step is to factor out the constant. So we'll factor out that 2 from the denominator. And then we'll do the same thing over here. And then we're in familiar territory.
I do have a question.
Yeah, sure.
Where does the 3 theta go?
Oh, why did I turn it to 2?
So should it be like a 6 there?
Yes, exactly. I completely was thinking that it was just exactly the same other than the trig function. So what we notice when we look here is that the pattern is that when we reduce the power, the angle of theta, whatever this angle is doubled. Whatever the angle here is, it's doubled. Thank you for pointing that out. So this angle right here, that angle, come on, you can do it. So that angle right there needs to be doubled. Thank you. So that should be a 6 theta. 6 theta, yeah, good question. So we always double the angle as we reduce the power. And then, again, like over there, bigger angle is no big deal. We just use reverse chain rule. So that's not a big, it's not going to be that crazy for us to deal with. So we have 1/2 the integral of a constant. Integral of 1 is going to be 1 theta. And then here, the integral of cosine is sine of the same angle. But then we have to divide by the derivative of the angle. Similarly over here, integral of 1 is theta. Integral of cosine is sine of the same angle. But then we divide by the derivative of the angle. So that's where we're at. You can leave those answers as is. You can expand this 1/2 and send it back across. Either way is totally fine. Does not matter. The reason that you'll probably see the answer written more in this form is that factoring out a constant from only 2 of the 3 terms doesn't give us a lick of advantage. We factor so that we can set to 0 and see what the zeros are. So this is the better answer, but if you left it like that, that's totally fine. This is the better answer because we never just factor out of 2 of the 3 terms. Like that's unless we're doing some special technique maybe, but
When you move the half on the first example to the outside of the integration, shouldn't the 1 in the inside be like fade away as well since you're doing half of that?
so we're factoring the 2 out of the denominator. So this 2 is coming out of the denominator, leaving 1 minus cosine.
Oh, okay, I see.
So this is under both of them.
Okay,
So when
yeah.
it comes out, the numerator is what's left.
Oh, okay. Okay.
Yeah, so you can distribute, you don't have to. You don't always have to have it in the best possible form. We have some flexibility there. But this would be generally preferred. Okay, so power reduction. So that's how we deal with even powers of sine and cosine. Power reduce. All right, so let's talk a little bit more about reverse chain rule. We've been doing it. I just want to sort of hammer it home one more time. You've done enough math in here now that hopefully this makes perfect sense. And the reason we use reverse chain rule is that it saves us time. It's efficient. Do you have to do it? No. But you all have started to realize as you're taking harder and harder classes, being efficient is a very good test-taking strategy. And if you're always going back to the roots of a technique, that's going to end up being very, very cumbersome. So here, if we look at this in Calc 1, you certainly would be expected to be doing this kind of thing. So there's your substitution, there's the derivative. As we go forward, it's very important. You're going to start losing points if you're not using good notation. So a couple of things. A, this should be an equal sign. That should be an equal sign, not an arrow or some other invented notation. These are equal. And if you have a du on this side, you have to have a dx on that side. So this right here is a differential equation. It's an equation with differentials. So that is a differential equation. And now we do our substitution. And so this integral will be equal to the integral of e to the u. And now we have the dx here. If we come back, you don't have to write out this step. Usually it's very intuitive. But our goal is to replace this dx with whatever it's equal to in terms of du. So du over -4, do it like that. That -4 is in the denominator, so we factor it to the front, and we're left with the integral of e to the u du. So this will be 1/4. The integral of e to the u is itself, plus a constant of integration. If the original independent variable is x, the final independent variable should be x, so we have to do our back substitution. So we're going to end up with e to the 3 minus 4x plus c. So that's how you would do it with substitution. That's the formal process for substitution. And it's not short. Anytime you do substitution, there are a fair number of steps there. With reverse chain rule, all we do is identify that the substitution is linear. And whenever the substitution is linear, we use reverse chain rule. Only when the substitution is linear. So I say to myself, the integral, I lost a minus sign up here, didn't I? There's a minus right there. And I got it sort of blocked out in here. And we put a minus sign right in there. So once we have identified that the exponent is linear, we know we can use reverse chain rule, and then we just say to ourselves, the integral of an exponential is itself divided by the derivative of the exponent. You can write it like that. That's totally fine. There's no problem with that answer. Or you could write it as -1/4. Doesn't matter. Both of those are equally good. But reverse chain rule, one step. Substitution, 1, 2, 3, 4, 5, 6, 7 steps until we got to the answer. So that's one of the things as you're moving up in math. Being efficient is a good strategy. It's a sound strategy. All right, so I'll do this one on the left with reverse chain rule. Actually, I already did that one coincidentally, so we'll just write it again. So here, first thing in your mind, you've identified that the angle is linear. That means you can use reverse chain rule. So you integrate the outer function. The outer function's integral is sine of the same angle. But then you divide by 5. That's the reverse chain rule part. So you all do the second one there using reverse chain rule. I'll highlight the substitution. With u sub, u is usually inside the square root, inside the angle, inside the exponent. So that's going to be your u if you were going to use u sub. But because that's linear, do it with reverse chain rule. If it helps you to see how to do it, sometimes using a rational exponent instead of that radical notation, sometimes that's a helpful thing to do. Totally up to you. Totally up to you. Okay. For you. Nathan, Sean. Eric. Will. All right. So when we see that one, maybe it's easier for you to realize that you can do reverse chain rule if it's in this form, because you can sort of see it as u to the 1/2. And the integral of a power of x, whether the power is integer or fractional, does not matter. You take your base, you add 1 to the exponent, you divide by the new exponent, and then the reverse chain rule says take the derivative of your substitution, which is 4, and divide by that 4. And so our simplified answer, we can cancel a 2 and a 2, so we would end up with 1/6 for x minus 1 raised to the 3/2 power plus c. So that's one that you're going to see quite a bit with that square root idea, so I just wanted to highlight that one. It's really quick and easy if you, once you see the process. Could you do it with substitution? Of course. You want to add those extra 6, 7 steps. If that's your jam, the more the merrier. You can do it the long way. All right, any questions on the concept of RCR, reverse chain rule? Again, it's only working with linear substitutions. Linear substitutions only, which happen very frequently. So it does give us a lot of, saves us a lot of steps. Okay, so this first section, we've looked at the integration tables a little bit, the integration table. Talked about power reduction, reverse chain rule. This section is all just sort of a hodgepodge of different integration ideas. So here's another one. We look at this integrand and we see a function that has negative exponents. Well, one negative exponent for sure. The key is to eliminate the negative exponents. So if we see some integrand and there's negative exponents, we want to get rid of them. And once again, the magic bullet is multiplying by 1. When you multiply by 1, you change the look but not the value. So I'm going to rewrite this with a little bit of space so that I can multiply by number 1. So we need to multiply by 1. What I want you to, let's see, that one is on the second. That one is on the fourth. Let's make this one a little bit smaller. Yeah, it looks like they upgraded the software. Do they tell us these things? No. One day, it's just different. One day, it's just different. So, what does anyone have an idea what the form of 1 could possibly be that would work here?
Is it e to the second z plus 4e to the negative?
Not that complicated. It's even simpler. So you're thinking kind of that conjugate model.
Yeah.
So it's even simpler. What about, let me ask you this. If we take e to the negative x and multiply by e to the x, what do we end up with? 1.
Because again, so it becomes e to the c.
So e to the negative x times e to the x is e to the negative x plus x, which is e to the 0, which is 1. You could also say to yourself that e to the negative x is 1 over e to the x. And if you multiply that by e to the x, you'll get 1. So however you can sort of algebraically see that that's true. So that's our trick here, is that we are going to multiply by e to the z over e to the z. So when that's distributed, in the numerator we're going to get what? Let's practice our algebra. E to the...
2z squared.
Nope.
3z.
3z. So powers with the same base, e to the whatever you add. So that's going to be e to the 3z. And then down here, e to the z distributes. E to the z times e to the 2z again is e to the 3z. And then here, what do we end up with? Minus 4. Because e to the z multiplied by e to the negative z is 1. 1 times negative 4 is negative 4. Make sense? So, question?
Yeah, so the reason why we went with e to the c is to remove the negative exponent, right? Because wouldn't that also be like a common factor thing? Or I'm overthinking it.
Yeah, we're just trying to get rid of the negative exponent, so we want to multiply by a power with the same base with the opposite exponent. So if it was e to the negative 2z, e to the negative 2z, we'd multiply by e to the 2z. Mm-hmm. So if we multiply by exactly e to the opposite, it will work. Now, what form is this almost in? It's almost in log form. What is the derivative of the denominator?
E to the 3c.
3e.
3e to the 3z. So we use our little magic wand. There's no 3 here, but we can make 1. Right? So now it's in log form. The derivative of that denominator is the numerator. But if we just throw a 3 in there, we need to be judicious and put a what on the outside?
1/3.
1/3, exactly. So once again, we're multiplying by 1. 3 over 3 is 1. Right? 1 is our magic bullet. You just have to have it in the right form. Now it's in log form, so we are done. Once it's in log form, we know that we integrate to the natural log of the absolute value of the denominator plus c. So that is how we integrate if we have negative exponents. All right, you all try that one. Hint, multiply by 1. Huge hint, right? Multiply by 1. key is going to be to figure out what form of 1 to multiply by. See a few yays. So y to what power? Y to the 3, y cubed. That is going to be the key. In the numerator, 1 times y cubed is y cubed. In the denominator, y cubed times y to the negative 1 is y squared. And then y cubed times y to the negative 3 is 1. So we're there. Okay. Now, we are at another nuanced situation. What kind of fraction is 5/2? Improper. What he said. If it's top heavy, it's improper. Right? A proper fraction, the numerator is less than the denominator. 1/3, 1/4, 2/5. Right? That's a fraction. That's what we think about. When someone says it's fractional, we're thinking less than 1. Right? That's kind of our intuition for what a fraction is. Something less than 1. It's a fractional piece. And if it's top heavy, like 5/2 or 9/4 or whatever, 11/9, if it's top heavy, if there's more on top, that's improper. This fraction, this rational fraction over here, this rational function right here, has a similar setup. The power on top is bigger than the power down below. It's top heavy. This is improper in the same sense. And back in grade school, what did you do with your 5/2? How did you write it?
2 1/2.
2.5, right? You did division. That's what we have to do here. All the algebra, long division. So in order to deal with this so-called improper fraction, we have to divide. All right, so now we have to remember how to do long division. So we take that denominator, we call it the divisor in this context. We want to divide it into that y cubed. We look at the leading term here. We ask ourselves what times y squared will give us y cubed. Answer y. So y times y cubed, y times y squared is y cubed. But we also have a plus y. And we are subtracting this quantity from above. So we have y cubed minus y cubed, which is 0. There's no y's up here, so we have 0y minus y, which is minus y. And as soon as we get to a situation where we have a proper remainder, so the power here is less than the power there, there's nothing we can put here that's going to give us this. As soon as that power is less, just like division, we're done. And so we're done with the division. So now we can rewrite this as that plus the remainder divided by the divisor. So now we've rewritten it into a way that is integrable. Yep.
Remind me again, when do we stop dividing?
As soon as this power is less than that power. If it's equal to, we still have to go one more step.
Right.
So we have to
But
get
you want to be less.
less. Yeah, strictly less.
So I am slightly confused by your answer there.
By this part here,
Yeah, I just don't entirely understand how you put it together.
So let's think about, if we go back, let's go to the 5 halves thing. If we do this, if we're doing our division, all right, we do 2 goes in, let's not pick 5 halves, because there's 2
I
2s.
can actually see where you're getting at, right?
Let's pick 7 halves. Are you seeing it?
Yeah.
So the 2 goes in here, how many times? 3, and then we subtract that off, and we would write this as 3 plus 1/2, and our shorthand notation for improper fractions is to write it as that mixed number, which really means 3 plus 1/2. So we do the dividend plus the remainder divided by the divisor. So we're doing the same thing here. The result is the dividend plus the remainder over the divisor. So same as you would do with division of numbers. Now this first function we can integrate easily. This is y squared divided by 2 minus, and I'm going to leave a little bit of space here. Let's handle this one on its own. So what form is this almost in? It's almost in log form. Derivative of denominator is 2y. All we have is a y up top. We use our magic wand. We want a 2y. We conjure a 2y. But there's a price to pay. If we conjure a 2 into the numerator, we need to pay the price. Got to balance it out. Divide by 2. Now it's in log form. We love log form because we know exactly what to do. This will be natural log, absolute value denominator, plus c. Do we need the absolute value bars in this case?
No, it's always going to be positive.
It's always going to be positive, so we actually don't need them. Is it okay? I would never take off for that. Those are equivalent. But that would be our preferred answer. Yeah?
I have a question. So you broke it up into 2.
Yep.
If you don't break it up into 2 and you try to do it in one step,
Yep.
you put the 2 at the top still.
Yes.
Wouldn't that bring it out to 1/2? And then that would make that y squared over
If
4?
you were going to do it in one step, what I would do is write a 2 here, and I would put parentheses here and put a 2 there, so that the log form is right here, so you can kind of see the 1/2, negative 1/2 multiplied by the integral of that. It's a little easier in this case to distribute the integral symbol so that it's sort of, because you don't want that 2 there to get mangled up with this y over here. You just want to be sticking with this fraction. So it's easier to break it into 2 separate integrals.
So I just had a confusion on where you got the y squared divided by 2.
The integral of y.
Oh, that's good. It's gonna be.
So we're going to
plus-
integrate this, so we add 1 to the exponent, divide by the new exponent.
Okay, and then you just gotta add up the integral.
Yeah, so we're using the
Oh, right, 'cause
the
you went from- okay.
power rule.
Okay.
You see it?
Yep.
All right. Let's go see if we can do one more, because I think that's the end of that page. So let's do one more example. Then we'll take our break. Okay, so here's another random technique. This is what's hard about integration. Like with derivatives, oh, there's a product. I'll use the product rule. Oh, there's a quotient. I'll use the quotient rule. Like it's very prescriptive. Integration, you just have to be a detective. And the only way to get better at becoming an integration detective is to do a bazillion of them. So here, we call this fraction splitting. When the denominator is a singleton, when it's a single expression, and the numerator is multi-termed, you can take that denominator and share it with the numerator. You can distribute it. You can split the fraction. That's what they're referring to. So we can split the fraction here. So we can make this the integral of 3x over the square root of 4 minus x squared dx plus the integral of 1 over the square root of 4 minus x squared dx. So you can split it into 2. So this works whenever your denominator is a singleton. You can share it with the numerator. Distribute it into each term in the numerator and split the fraction. So we split the fraction and we can distribute the integral. Okay. Now, the integral on the right, that's one that we're going to get more and more familiar with. That's the form of an arc sine, an inverse sine. So that one is immediate from our integration table for inverse sine. We'll talk about why it is what it is in the near future. What technique can we use for this first one?
Pull out the 3.
Pull out the 3, and then we have the same question. Then how do we integrate?
You saw?
U sub. U sub. U sub is going to be the way. Now we can't use reverse chain rule. The substitution is always what's inside the square root, what's in the exponent, what's in the angle. Is that thing linear? No.
That's quadratic.
Linear, not linear. So we cannot use reverse chain rule in any way. And what our mental check is, if we think substitution, we let u be whatever we think it's going to be, and then we, bless you, then we think about the derivative, and the derivative has to be present outside of the square root. And maybe not exactly, it just has to match the power. It's got to be a multiple of the derivative. And by that, what I'm saying is, oh, we have a quadratic. Its derivative is linear, negative 2x, it's linear. And that numerator is linear. We can make it match. Right? So if the derivative is if the u sub is a quadratic, its derivative is linear, and we have a linear function of x waiting to get taken out with u's. So let's see. So we're going to let u equal 4 minus x to the 2, take the derivative, and we have that. Most of us, the book tries to be clever sometimes. My recommendation is just to say, hey, there's an x dx, there's an x dx. Let's isolate the x dx. So we have du over negative 2 is x dx. So if we factor that 3 out, x dx will get replaced with du over negative 2. Sometimes at the book, if you look at the help me solve this, they'll start doing all this weird manipulation to try to make 3x dx down here. It's just easier. Solve for x dx, plug it in, and combine the numbers. To force this to become positive 3x dx just takes a little bit of work. You have to multiply both sides by negative 3/2. And it's just a little bit of, it's unnecessary busy work. So we're just going to substitute it in. So we're factoring the 3 out. So the 3 is coming to the front. We have the integral. X dx up in the numerator, that's going to be du over negative 2. You all know by now that if you're dividing by negative 2 on the inside of the integral, that negative, you can just factor out to the denominator in the front. So all we have then left up here is the du. And now the yellow down below, that was u, so we're going to have u to the 1/2 in the denominator. So that's what it'll look like once we convert to u. So, negative 3/2. What's the best way to write this so that we can integrate it?
U to the negative 1/2.
U to the negative 1/2, so we're going to bump it up to the numerator. And when we move things like this around, we have to change the sign on the exponent. Now we can integrate it. Now we can use our power rule. So we'll end up with -3/2 multiplied by, we add 1 to the exponent. Adding 1 to -1/2 gives +1/2. Dividing by +1/2 means multiplying by 2. We add a constant of integration. And then our final step, we have to do some back substitution. We want to get back to an independent variable of x. U is 4 minus x squared. Oh, and I lost out the inverse sign piece of this. Let me get that inverse sign piece put in here. All right, let's move this over. We need the inverse sign in here also. Let's move you to there. Okay, so this second integral, what's going to be that antiderivative? So if we integrate that according to this rule up here,
1x over 2.
so plus inverse sine of x divided by 2. Everyone agree? So 2 is the base here when you put it into a square form. So that's 2 squared. Now I didn't put the plus c there because I know the plus c is coming from this indefinite integral here. So then we can just sort of wait with the plus c. We can put it in now or wait. We know it's coming. And so then here the plus c has arrived. We're going to put our inverse sine of x divided by 2 plus c. We've simplified, and then this is our final answer. Plus c. All right, is there any piece that you want to ask about? Yeah.
The 2u half came from the antiderivative of u negative half, right?
Mm-hmm.
Okay.
So we add 1 to that and divide by 1/2. And when you divide by 1/2, you multiply by 2.
Okay.
Dividing by 1/2. All right, ready for a break? All right, let's take 10. Take 10. The new worksheet is released into your OneNote area. You can start looking at that. One thing I'll say about the old worksheet is that the concepts in those worksheets are the basic concepts. And you're not going to do well in any exam if you can't do the basic concepts from the worksheet. I would highly recommend looking carefully at the lesson in those worksheets and working on those like right from the start, because those things are meant to just grab the highlights, the important fundamental pieces to all of these ideas. So take a look at the answer key. The answer key is released also. So take a look at that and let me know if you have questions. All right, let's take 10. Is it really snowing tonight?
Wouldn't surprise me.
I've been looking at my weather app every day and mine's not showing that. It's like, I need a better weather app. Maybe that person was fired. Okay, so let's go to one of these things. So here's another one. This is one that I find is sort of it doesn't just jump out at you as easily as some of the other ones. Like you see the negative exponents and those kind of jump out. Oh, I got to get rid of the negative exponents. Kind of jumps out at you. The fraction splitting is perhaps a little more obvious because the denominator has to be one term. You have to treat it as one term and distribute it. But this whole improper fraction thing, it's very easy to sort of not see it right away. So it's just one of those ones that you have to kind of have on your radar. So when we look at that, we have two choices here. We could use a fraction splitting technique first. If we wanted to, we could take that denominator and treat the denominator as a singleton, as one term, and we could do a distribution like this. So this is a possibility as a way to start. Or we can just do long division. Both are going to come up with the same answer. Or we can just do straight up long division right from the get-go. Doesn't matter. Does not matter. Yeah, let's just do long division right from the start. We have to do long division. Let's just see what happens right away. So we're going to have x squared plus 4. And we need to write this in descending form, like that. So negative x to the 4th plus 6. I'm leaving a little space because maybe we're going to have some x squareds in there that we need to deal with. So 0x squared. Let's see what happens. We multiply by what to get to the negative x to the 4th?
Negative x squared.
We're going to multiply by negative x squared. So that's going to give us negative x to the 4th minus 4x squared. And we are subtracting that. Now I see a lot of people sort of just change these signs and then add, which is fine if you're super meticulous. But if you make any mistake, it's hard to find the mistake later on. So I usually just leave a minus out in front, but whatever works. So negative x squared, negative x to the 4th minus a minus is plus x to the 4th, so that's 0. And then right here, we can kind of think in our mind that there's 0x squared there. So 0x squared minus minus is plus. So 0 plus 4x squared gives us 4x squared. And then we can drop that 6. So we're not done yet because the powers are matching. We go until the power under here is less. So it's not less yet. So what are we going to do? What times x squared gives us that?
Negative 4.
Positive
Positive
4.
4, sorry.
We want it to match,
Right.
because then we're going to subtract it off.
Right.
So we want it to match. So that's going to be 4x squared plus 16. And then we're subtracting that off. So we're going to subtract that off. And when we subtract that off, 4x squared minus 4x squared is 0. 6 minus positive 16. So 6 minus 16, negative 10. All right, so now we're done. So our integral is going to be equal to the divisor, which is negative x squared plus 4. That's the divisor. Plus the remainder, that's the dividend. Dividend, did I say divisor? Dividend. So it's the dividend, whatever's up here, plus the remainder over the divisor. So minus 10 over x squared plus 4. So now we have something that is integrable. And that one on the right over there, did I put it up here? I didn't put it up there. So do you know what form this one is going to end up being? Let's get over to it. Let's integrate the first two terms and just rewrite it like this. So we integrated the first two terms. What is that one? Arc tangent. So the sum of squares in the bottom is tangent, arctangent. And you can kind of remember that if it's a sum, the plus looks kind of like a T, arctangent, whatever it takes to memorize that. So let's take a look for a second. So if we go back here, so arctangent, the one that integrates to arctangent, I want to point this out because you've got to be a little bit cautious. When we're dealing with an A in here, let's take a look at both of these. So the inverse, both of them are going to have the inverse trig function of x over A. That's common. But notice that the inverse tangent also has a 1 over A in front The inverse sine does not have the 1 over a in front. The inverse secant also has the 1 over a in front. And we're going to learn a technique that's going to sort of take care of that for us. But when you're just using the integration tables, you just need to sort of notice that inverse sine doesn't have the 1 over a like the other two do have. So just keep that in mind. So we are going to end up with minus 1/3 x cubed plus 4 times x minus, let's see. So what is a in this case? 2. So we're going to have a 1 over 2 in front, which is going to make that a 5 inverse tangent of x over a plus c. On my phone that made a noise? Delayed opening on, oh my fry. We live in Colorado. Come on, man. We used to go years without having any sort of delayed opening or canceled classes. Like now it's like every semester. Oh my gosh, it might snow. Come on. All right, so any issue there? Everyone see that the arctan has the 1/2 in front of it, so the 10 divided by 2 gives the 5. And it's always, whatever the inverse trig function is, it's always going to be x over whatever the square root of that number is. All right.
Okay.
You see it?
Yeah.
Complete the square. Oh, more algebra. Lovely. Calc 2 is where all your algebra and trig holes come to roost. Oh, there's the inverse tangent formula. Okay, look at that denominator. And we say, ooh, maybe that denominator factors like a perfect square trinomial would factor, but it's not a perfect square trinomial, unfortunately. So we have to complete the square here. So we will have 0 to 2. And you all remember, what is the key to complete the square? How do we figure out, so we're looking at these first two terms right here. How do we know what the constant needs to be in order to complete the square?
It's going to be 1/2 of it squared.
Exactly. So we take the coefficient of x, divide it by 2, and square. That's what we need the constant to be to force it to be a perfect square trinomial. So what we can do is borrow from the 8. So we look at this x squared plus 4x. We take that coefficient right there, divide it by 2 and square, get a 4. So we need a 4 to make this a perfect square trinomial. So we can say, oh, well, let's borrow 4 from the 8. So then we have this. That part right there is a perfect square trinomial. So that will factor into x plus 2 quantity squared. Okay. All right, let's see where we're at. So we have a definite integral, 0 to 2. We have x in the numerator. Now we have x plus 2 quantity squared plus 4 dx. Okay. So, what do you think?
Substitution.
Substitution is a great strategy. So the first thing, if we don't see an immediate antiderivative, you should be asking yourself, will substitution work? And substitution is going to work here. And let me just point out that this is not an inverse tangent because the numerator is an x. Right? The inverse tangent one, maybe we'll get to an inverse tangent eventually, but right now, right, there's no x up there. So there's no x up there, there's an x there. So this is not an inverse tangent. If that was just a constant, it would be inverse tangent. But it's not, there's an x. So let's go with substitution. That's always sort of the best choice if right out of the gate, see if substitution will work. Derivative of both sides, we get du equals dx. All right, interesting. Interesting. So the limits are now u limits, so we don't want to put the 0 in the 2 unless we've checked. So let's see. Let's first do the substitution. All right, well, x plus 2 is u. So down here we've got u squared plus 4. Du and dx are the same thing. How about this numerator? That needs to be converted to a u. Any idea what that would be?
U minus 2.
Exactly. If you look right here, this is the equation that relates the u's and the x's. We don't know what x is, but if we look right here, we see that, oh, if we isolate x, x is u minus 2. So that's going to become a u minus 2. How about limits of integration? If x is 0, what is u equal to? 2. If x is 2, what is u equal to? 4. So we can do that. So we're plugging both of these in right there in order to get the u limits. All right, so now what we're going to do is treat this denominator like it's one thing, a singleton, and we are going to distribute it to the numerator. We're going to split this fraction. If we split the fraction, what I see right now is that if we erase the 2, what form is that almost in?
Natural log.
Almost in natural log form. And if we erase the u, what form is that in?
Tangent.
Inverse tangent, yeah. So splitting the fraction is going to be our next step. So we're going to say integral from 2 to 4 of u divided by u squared plus 4 du. And we can factor out the negative 2 to the front of this second integral. So we're going to have du over u squared plus 4. To put the first integral in log form, we're saying, oh, let's multiply by 2 and 1/2. So we're multiplying by 1, our magic bullet. Fixes everything. And now we're ready for our integration. So over here, we've got the 1/2 out in front. So we're going to end up with 1/2 natural log. Absolute value of the denominator. The denominator is always positive, so I'm not even going to put the absolute values here. So we've got that. Minus. They're all going to be evaluated from 2 to 4, so we can put the whole evaluation symbol at the end. That's in the arctan form. What is A for that one? 2. So with arctan, we have to divide by 2. We're going to have a 2 divided by 2. So we're going to have 2 over 2. Well, let's write it just to make sure you're seeing it. 2 over 2, arctangent of x divided by a, u, we're dealing with u. U divided by a, so u over 2. And then this is all evaluated with the u limits, 2 to 4. Good, bad?
Question, why is it 2?
Why is it what?
When you were writing the natural log and the tangents, why is the 8 the 2?
Say that again. Why is the 8 the 2?
The A, the letter
The A. Sorry. The A is 2 because it's whatever is below the square. So when we look here, this is 2 squared.
Okay.
So this is x squared plus a squared, or u squared plus a squared. So this is u squared plus 2 squared.
Okay.
So a is whatever the square root of the constant is.
So if that was say like 16, that would make it 4.
4,
Okay.
exactly. Correct. 100%. So now let's plug in a 4. So we're going to have 1/2 natural log. Plugging in 4. 4 squared is 16 plus 4 is 20. So natural log of 20 minus inverse tangent of 4 divided by 2 is 2. So that's the upper limit. And then we subtract off the lower limit. So minus 1/2 natural log of 8. Minus a minus is plus, inverse tangent of 1. Okay. This one can be simplified. Arctan of 1. So remember that inverse trig functions are angles. Inverse cosine is on top of the unit circle. It's an angle between 0 and 180 degrees, 0 and pi radians. Inverse sine and inverse tangent are on the right side of the unit circle. So they go between negative pi over 2 and pi over 2. So when you see this, you say to yourself, angle on the right with a tangent value of 1. What angle on the right side of the unit circle has a tangent value of 1?
Pi over 4.
Pi over 4. Angle on the right with a tangent value of 1 is pi fourths. Inverse tangent only has, there's not a lot that we know with inverse tangent. It's like, okay, root 3 over 3. Inverse tangent of 2. Do we know an angle on the right that has a slope? Tangent and slope are the same thing when you're on the unit circle, y over x. Do we know an angle on the right side of the unit circle with a tangent value of 2? When we think about our 12-sector circle, root 3 over 2 and 1/2, none of those fractions are going to form a 2. So that one we cannot do anything with. We can combine these two logs. We're subtracting. We could factor the half to the front, and then we have log 20 minus log 8. How do we combine a subtraction of logs? Log 20 over log 8. Log 20 minus log 8 is fraction log of 20 over 8. So we can write this as 1/2 log of 20 over 8 minus inverse tangent of 2. That we can't simplify. But then arctan of 1 is pi over 4. And then in here, we could say, oh, divide out of 4, divide out of 4. And that will be about as far as we can go. Okay, now, you brought up the idea of conjugates. Here's where conjugates come into play. So with trig functions, we know our Pythagorean identities. And we know that in the Pythagorean identities, the trig functions are always squared. We know that we could replace sine squared with 1 minus cosine squared. We could replace cosine squared with 1 minus sine squared. We know that 1 plus tangent squared is secant squared. So secant squared minus 1 is tangent squared. Like there's all those identities. The key, though, is that all three of those Pythagorean identities, we have a square. So we can't do diddly right now with this not being a square. And so what we do to force it to be a square is the following. So we're going to take our integrand, and if we multiply once again by 1, and the form of 1 that we are going to multiply by is the conjugate of 1 minus cosecant. So we multiply by 1 plus cosecant over 1 plus cosecant. Let's see what happens. So this is going to give us a numerator of 1 plus cosecant of theta. And in the denominator, we have 1 minus cosecant squared theta.
What
Why do we have two d thetas on the top?
That's a great question. They're multiplying. Thank you. Yeah, we only need one. And it should be on the outside. Yeah, I shouldn't have put it in that numerator. That's too weird. Okay, so now we have that. And let's remind ourselves what the identities are. And if we look at our Pythagorean identities, there is the primary one, sine squared plus cosine squared is 1. We're looking for the one that has cosecants. What do we have to divide the primary by to get to cosecants?
1 divided by sine.
So if we divide everything by sine squared, we will get the one that we need. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. 1 divided by sine squared is cosecant squared. So that's the identity we need. And if you subtract the cosecant squared to the left and subtract the cotangent squared to the right, we'll end up with this denominator matching. So we have 1, let's see, 1 plus cosecant of theta. So what do we end up with in that denominator if we use that identity? 1 minus cosecant squared? Minus cotangent squared?
Yeah.
Negative cotan squared? Everyone seeing that? So this will be negative cotan squared of theta.
And that's the trigonometry identity, right? Or
Yes.
is it- Okay.
Yep, so using the Pythagorean identity. Okay, so now we have that. All right, so now let's split the fraction. Now the denominator is a singleton. It's one term. We can split the fraction. So this is going to be minus the integral. What is 1 divided by cotan squared? The reciprocal of cotan is
Tan.
tangent, so tan squared. 1 over cotangent squared is going to be tangent squared. So we've got that. And we're going to split into 2 separate integrals. So the minus cotan squared is dividing into each. So the second integral is going to be cosecant over cotangent squared. Probably some cancellation there. Probably easiest if we convert those all to sines and cosines. Right? So we have cosecant, which we know is 1 over sine. And then we're dividing by cotangent squared. So that's going to be multiplying by the reciprocal. The reciprocal is tangent squared, so sine squared over cosine squared. So there. So we've now split it. We've now done that split where we did minus cotangent squared into 1 and minus cotangent squared into cosecant. So let's see if that helps us. What's the integral of tan squared? Do we know that? We don't know that, do we? Which one do we know that has a square? Secant squared. Right? Derivative of tangent is secant squared, so the integral of secant squared is tangent. Can we turn that tangent squared into secants? The answer is yes. Let me show you the most important triangle around. So this triangle is the best way to remember the relationship between tangent and secant. So if you extend, if we're on a unit circle, and you extend the terminal ray so that it's directly above the point 1, 0, here is what we end up with. This is a picture of tangent. This height is tangent, and this diagonal is secant. That is the best way to remember the identity. Tangent is the vertical leg, secant is the hypotenuse, and we see very clearly that 1 plus tan squared is secant squared, Pythagorean theorem. Now, the question may be in your mind, well, why is that true? Sure, okay, if that's true, why is it true? Let me draw a red triangle right here. And then let me pull that red triangle out just so that it's neater. Still theta is right there. What is the base of this red triangle? If we're on the unit circle, so the green is 1 all the way across, so now the hypotenuse is 1. All right, so it's in the unit circle. What is the x direction? What is the y direction? On the unit circle. X is cosine theta. So this dimension is cosine theta. This dimension is sine theta. Do you agree that the red triangle and the green triangle are similar? In other words, they have the same angles? A pair of triangles that have the same angles have the same ratios. So if we have 2 triangles that have the same angles, all the ratios have to match. For the red triangle, what is rise over run equal to?
Tangent.
Tangent. The rise is sine, the run is cosine. The slope, in other words, is rise over run. It's sine over cosine, which is tangent. That tells us with the green triangle, the rise over the run has to also be tangent. They must be equal. They're similar triangles. But the run on the green triangle is 1. So we need the rise over the run to be tangent. Well, if the run is 1, the rise has to be tangent. This over this must equal this over this. And if that is tangent, we know the identity if we go back and do this kind of thing. Tan squared plus 1 is secant. Tan squared plus 1 is secant squared. So the hypotenuse has to be secant. So then we can see this is just an easy visualization to remember that 1 plus tan squared is secant squared. So in other words, tangent squared is secant squared minus 1. So that's what we can do over here. So we can make this secant squared minus 1 d theta. And that's integrable, because the integral of secant squared is tangent. All right, let's keep on trucking here. So our second integral, we're going to cancel out a sign with the numerator sign. And we have that. Okay. With that second integral, do you see a u substitution that would work? U equals cosine. Because the derivative of cosine is negative sine, and that's in the numerator. All we need is a multiple of that derivative to be present. That is going to be the key here. If we let u be cosine, then du will be minus sine of theta d theta. We can move the minus sign over here. And now we're matching the numerator exactly, sine theta d theta.
Would reverse chain rule work if we rewrote the cosine as sine squared minus 1?
No, because the derivative of sine squared is 2 sine times cosine.
Okay.
Right? Remember that if you have a power on a trig function, when you differentiate, the power comes down, you subtract 1, but then you have to multiply by the derivative of the base, so you get that chain rule. The chain rule, dragging it into the muck. Okay, so here, integral of secant squared, tangent. This minus distributes here. We're going to integrate plus 1. That's just theta. This is going to be the integral of, let's see, sine theta d theta. That's minus du. So this is going to become plus du on the inside. cosine squared becomes u squared in the denominator, what does it become in the numerator? U to the negative 2? So if cosine theta is u, in the denominator we have u squared, but we can't integrate something in the denominator, so we have to move it to the numerator by changing the sign to the opposite. So we get that. So we're almost there. So we have minus tangent theta plus theta. Integral here, we add 1 to the exponent, divide by the new exponent, put a constant of integration. And then we have to do our back substitution. So we have minus tangent theta plus theta minus 1 uth. So minus 1 over u. 1 over u is 1 over cosine. And what function is 1 over cosine? Secant. Plus c. So there is, long story long. That's our antiderivative. More correctly, family of antiderivatives. Yeah, that was long. Yeek! Trig! Gotta practice your trig. Every page of Calc 2, every page of Calc 3, trig. Any step there that you want to ask about? Biggest thing with these is practice, because there's not a bunch of rules. It's like with derivatives, there's rules. With integration, you just got to try stuff.
So, secant squared theta minus 1 is the antiderivative of negative tangent theta?
This right here,
Mm-hmm.
this is just an identity.
Right.
Tangent squared equals secant squared minus 1.
Right,
And then the antiderivative of secant squared is tangent.
Right, okay.
The antiderivative of 1 is theta.
Okay, cool.
Yeah, so this is Pythagorean identity, and then that is the antiderivative. All right. Horrible word, miscellaneous. Miscellaneous, okay. So, let's see. So we have these two miscellaneous ones. The natural choice for u when you're substituting is to let u be what's inside the root, what's inside the angle, what's inside the exponent. Right? Those are the typical places. And we look here, and this, if u sub is going to work, that is the natural choice. That's what's inside the main square root. Let's see what happens. So if we take du, we will get derivative of 1 is 0, and then here we get 1/2 x to the minus 1/2. Right, bring down the half, subtract 1. So we get that. And if we wanted to, we could write this as 1 over 2 root x. All right, so there is that's our du. Let's see what happens over here. So this is going to be the integral of the square root of u. All right, 1 plus root x is u. 1 plus root x is u. Now the dx needs to be replaced. So the dx needs to be replaced. Let's isolate the dx here. So dx is going to be 2 root x du. Okay. So if we replace this dx with that, then we're commingling x's and u's, which we cannot do. We cannot commingle. We need this to be only u's. What do you think we can do?
Substitute root of x for u.
Are you saying up here?
Yes.
So if we look right up here, the root of x is equal to u minus 1. Exactly. So that is what we need to do. So this is going to be 2u minus 1 du. Now we have dx completely replaced with an expression that only has a u in it. So now we're golden. Ish. So 2 times u minus 1 du. How about limits of integration? If u is given by this expression, what is u equal to when x is 0? 1. What is u equal to when x is 1? 2. So those are our new limits of integration. We go to that u-x relationship, plug in the x, get the u. All right, now let's try to put this in a workable form. We can obviously factor out the 2. Now we have to distribute the square root of u to each of these terms, so we're going to end up with u to the 3/2 minus u to the 1/2 du. And once we have those fractional exponents, we breathe a sigh of relief because we know how to add 1 and divide by the new exponent. So we add 1, we get 5/2, divide by 5/2 means multiply by 2/5. We get 2/5 u to the 5/2 minus, add 1 to the exponent, get 3/2, divide by 3/2, get 2/3. And this is from 1 to 2. So this will equal. I'm going to distribute this 2 right here and make that a 4/5. Leave a little gap, and then this is going to be a 4/3 here. So distribute that 2. All right, so we're going to plug in the 2 first. If we plug in the 2 right here, we get the square root of 2 to the 5th. Square root of 2 to the 5th means square root of 2 5 times, which is going to be 4 root 2. We get 4 root 2 minus 4/3. Here, square root of 2 3 times is 2 root 2. So that's everything with the 2 replaced in. Then we have to subtract off everything with the 1 put in. So again, let's just distribute that 2, so we have 4/5. And what happens when we plug in a 1 into either of these places? We get just 1. So we're going to get 4/5 times 1, and we're subtracting. So we subtract that, makes plus 4/3 times 1. So that is where we're at. That is where we are at. We need a little more space down there. Let's do a little more just to make sure. Okay, so let's see what we can simplify. So that's going to be 16 root 2 over 5. That's going to be minus 8 root 2 over 3. That's going to be minus 12 if I multiply top and bottom by 3 and then multiply top and bottom by 5. We get that. And then we have to do the same thing over here. We need to multiply this by 3 and 3, multiply this by 5 and 5. And hopefully this will be enough. Okay. So we're going to end up with 15 as our common denominator for everything. This is going to be 48 minus 40. 48 minus 40 is 8 root 2. This is going to be 8. And that's about it. If we wanted to factor out the 8, we could. We don't have to, but we could. We could make this 8/15 So those are, assuming there's no arithmetic mistakes there. Question?
Yeah, can you explain the process again when, on the u3 minus the u in half? How you got to the 2/5 and the power of 5/2?
These right here. Did you say these coefficients?
Yeah,
Add 1 to the exponent,
right, okay.
so you get 5 halves. And dividing by 5 halves means multiplying by 2/5.
Right, okay.
So we're going to add 1 to each of these. So I'm going to add 2/2 here to get 3/2. And if we divide by 3/2, we flip it to multiply by 2/3.
Okay.
So anytime we're dividing by a fraction, we multiply by the reciprocal. All right, let's do the last one here in this section. They give us a hint, or I give you a hint. Power reduction backwards. So power reduction, remember that cosine squared of, let's just say x, is going to equal 1 plus cosine of 2x divided by 2. So this one's a little weird. Now some of you are still sort of hasn't been beaten out of you yet that you cannot separate a square root over a sum. That needs to be beaten out of you. You need to beat it out of yourself. I saw it a couple of times on the test, more than twice. You cannot separate a square root when there's a plus or a minus down below. You can separate a square root if there's a product. Square root of AB is square root of A times square root of B. But square root of A plus B, you can't do anything with that. You can't break that square root apart. Beat that out of your head. So that's called the freshman dream, that you can just distribute the square root. So what we notice, though, the hint is telling us that, hey, look at that radicand and look at that numerator. Those match. So we can use our power reduction in a clever way. We can say, oh, well, this is really the square root of 2 cosine squared of x. 2 cosine squared of x dx. What is the square root of x squared?
Absolute x.
Yes. Good man. That is the first time someone has answered that correctly in a long time. That is not just x. It depends on whether x is negative or positive. If you take -2 and replace that for x. So if I let x be -2, this becomes the positive square root of 4, which is positive 2. The square root symbol means the positive square root. These numbers are not the same. The square root of x squared is only equal to x if x is positive. The square root of cosine squared is only cosine if cosine is positive. When we look on this interval, that puts us in quadrant 1, where cosine is in fact positive. So in this case, because cosine is positive, we can use the shortcut here and say that this is integral, that's going to be square root of 2 cosine of x. We can do that because cosine is positive on that interval. If that interval went from pi over 2 to pi, we would have to multiply this by -1. Because in quadrant 2, cosine is negative, so we would have to do a modification. This we can integrate. Integral of cosine is sine. 0 to pi over 2. Sine of 0 is 0, so that's not going to contribute. Sine of pi over 2 is 1, so our final answer is square root of 2. Yeah, important to start thinking about these things. Square root of x squared is not always x. All right, let's go ahead and take a gander into our first new integration technique. So 8.1 is just a bunch of random miscellaneous things, special cases, which is hard because they're so sort of random. Improper fraction, completing the square, change all the negative exponents to positive. That's harder than this because this is much more like algebra. This, we have a prescriptive way to deal with it. So most of you have probably heard about integration by parts, casually named ultraviolet voodoo. Ultraviolet voodoo gives us a way to remember the formula. So the formula, if we're integrating with integration by parts, this formula on the right is what we need. Ultraviolet voodoo. So that's how people remember it. UV minus the integral of V du, ultraviolet voodoo. And ultraviolet voodoo is essentially a reverse product rule. So in Calc 1, if you have a product and you have to differentiate, you use the product rule. First derivative, second, plus blah, blah, blah. All right? So now we want to integrate a product. That's what integration by parts will do primarily. That's kind of the core of integration by parts. It allows us to integrate a product where regular substitution doesn't work. We've already integrated lots of products in here where substitution worked. But if substitution doesn't work and we're trying to integrate a product, integration by parts is going to be the key. So when we say in math a sum, that also includes negatives, right? You can add a negative number, like a sum and a difference. But a lot of times we'll just say a sum. When we say a product, it's the same thing. Division is a product. This is x times 1 divided by the square root of 1 plus x. Right? So when we say a product, it doesn't have to look like that. It could look like that. It could be in a fractional form. It's just the first one times the reciprocal of the second one. So when we say integration by parts is good for products, we also mean quotients. So here's what we're going to do. And integration by parts is a learned technique that just takes some practice. And if you do it the same way every single time, it's going to get really routine and it's going to feel like not a big deal. So I will always do this. The idea is that we want to create from our integrand a UDV. So I'm going to put this in a little table, and my UDV is always going to be the top. And so the idea is that U times dV is the integrand, including the differential, the dx. So I want to identify a U and a dV. So I'm just parsing. Looking at that integrand, I'm just going to parse it. I'm going to say, okay, well, what are my choices? So the dx obviously has to go over here. The differentials have to stick together because our goal is going to then be on this, in this column to create a du, take a derivative, and in this column take an integral. And the only way we could take an integral over here is if we have a dx and a dv in the equation. So here are my choices. I could put x dx over here and 1 over that thing right there. That's one choice. That's one choice. Another choice would be to put the square root over here and the x over here. That's also a choice. So we could also do this. So do you see, first off, that that times that gives us our integrand? So that's all we're doing is trying to subdivide the integrand into like two factors that multiply together. So we could do that one. Or the only other choice, we only have two choices. The only other choice would be to do this and do that. Okay? Those are the only two choices. Here is the main guideline. We know that we are going to want to turn this into a uv minus integral of v du. That's what we're going to want. And the only way it's going to work is if this new integral is easier than the old integral. It's the only way it's going to work. To know whether I should put the x here or the x there, the 1 over root here or there, there's no way at this stage you're going to say, oh, this one's going to work. You have to get comfortable with trial and error. You try one, if it doesn't work, you erase it and try the other. You have to get comfortable with that. There's no way to develop the insight yet to be able to say, oh, this is going to work for sure. So you've got to just get into the habit of trying things. And there's some patterns that will emerge for sure. So let's try this one and see what happens. So now we differentiate both sides here. We get du is equal to dx. One basic rule that I think helps is that over here with the integration thing, if you can pick the largest chunk of the integrand that you can integrate easily, that usually is a pretty good mental note. The biggest piece that you can integrate easily. All right, so how do we integrate that? We might have to come off to the side. So if we want to integrate this, we are going to do what we always do, put it in the numerator. So we would have that. And then we use the power rule. Add 1 to the exponent, divide by the new exponent. And then use reverse chain rule if necessary. So this is x plus 1 to the positive 1/2 divided by 1/2. And there's plus c there. Okay. The reverse chain rule is just the division by 1, so doesn't appear. So that's what goes here then. So 2, and I'll write it as a square root, just, I don't know why. So we have that. We do not need the constant. You can always choose the constant to be 0 in this context. So we don't have to deal with a plus c here. You could pick any constant you want. I will always pick 0. If you want to pick pi for your constant, be my guest. It will all work out. So there is the integral of this function. You can choose whatever constant you want. I choose 0. So we have that. Now we have to see if what we get is something simpler than what we started with. So I'm going to call this, it's helpful to identify this whole original thing as a letter so that we can just rewrite it down below. You can call it whatever letter you want. Most books will use a capital I. I prefer to use capital Omega because one semester, that's just what happened. And I've stuck with it, and it feels like a good, easy to remember thing for integration by parts. So there's our original integral. We're just going to call it omega. Now we're going to form this. uv, so that's 2x square root x plus 1, uv, minus the integral. So uv is this main diagonal right here. We're taking that multiplied by that, uv, main diagonal, minus the bottom row. Bless you. VDU is down here. So now we're just going to subtract off the bottom row. So this and that, dx. So there's our new integral, uv minus integral of VDU. Can we integrate that? Darn straight. That's easy to integrate. That's easier than the original, so we're golden. So we have made a correct choice. The other choice might also work. Sometimes both choices work, sometimes one works. Sometimes one's a lot easier than the other. There's no real way to tell at this stage of the game. So now let's make sure we can integrate this properly. So we have x plus 1 to the positive 1/2. So this is going to be x plus 1 to the positive 3/2, adding 1. Divide by 3/2 means multiply by 2/3. Reverse chain rule, multiply by the derivative of what's in here. Derivative is just 1, so it doesn't matter. And then we put our generic constant of integration. There is our answer. And yes, you're going to make that 4/3. Make that 4/3. So that is integration by parts. Ultraviolet voodoo. Are we done right now? Yeah, we're done. So, yeah. Over the weekend, look at your exam. Now is the best time to look at that exam. Look at the worksheet. Make sure that you understand the key to the worksheet. And then start up on chapter 8. Start doing some integration by parts. Start doing some voodoo. It's a great technique. It's going to lead us to all sorts of cool places.
So earlier question.
Let me hit pause on this recording. And then I will